31, 32, and 34. So the questions that we want to address is, what are the reasons for these changes in nuclear structure, and what happens for heavier nuclei out here, which are very important if we want to explain nuclear synthesis in the upper. So how can the nuclear structure change when we go away from the value of stability? One possible explanation for that is given by the monopole part of the tensor interaction. And this interaction acts between protons and neutrons, and it depends on whether they are in L minus 1/2 or L plus 1/2 orbits. If they are in opposite orbits, then this force is attractive, and as a result, the orbital is more bound. If they're in the same kind of orbit, the force is repulsive, and the orbital is less bound. So if we look over here, I plot the effective single particle energy as a function of the proton number for the n equals 20 isotopes as an example. And on the very right side here, we have calcium-14 with 20 neutrons and 20 protons. And the proton orbitals d5-half, s1-half, and d3-half are all fully occupied. And you can see that there's a large gap between the neutron d3-half orbit in red and the FP shell above that. If we now remove protons from calcium-40 and go to more neutron-rich nuclei, and starting here, magnesium, we remove the neutrons from proton d5-half orbit. And this is the partner of the neutron d3-half orbit in red. And the slope of the effective single particle energy then changes. And as a result, the shell gap at 20 is closed, and the new gap at neutron number 16 appears. As you can see also in this plot, now again the effective single particle energy as a function of the neutron number for the oxygen isotopes. If we start with oxygen 16 here and we add neutrons, and neutron number 16, oxygen 24, the s1-half orbit is fully occupied, and the next neutron would go into the d3-half orbit, which is way higher in energy. This is a large energy gap, and it's also unbound. So this explains why oxygen 24 is the doubly magic nucleus with a new magic number n equals 16. So in general, we can say in stable nuclei, where neutron and proton number are similar, neutrons and protons occupy orbits, and as a result, the proton J upper orbit is occupied, leading to a lowering of the neutron J lower orbit.